Right. I was saying, Mr. Chewe, are you able to get me?
Yes, sir.
Great. Mr. Batala. Awesome. Thank you. So here we're saying that in work energy and power, this is the practical one. The application, of course, even the other one was practical, but that one was the foundation. So first thing you can see is that we're looking at a typical example of a vehicle moving on a road. The kind of forces you expect include friction between the road surface and the wheels, the slope, yes, the tires, correct, and air resistance, and also the accelerating force, which is due to the speed increasing. So this is what you see below here. Here we are calling it E or T, I call it a small letter E is equal to the R plus W sine theta. Now why we call it W sine theta? This is the amount, or rather, a component of gravity. Now let's just do an experiment. Are we having calculators there?
Yes.
Great.
Yes.
So, what is, try to enter sine 90, see what it gives you. Very good. But here, okay, great. So, sine 90 afumya 1. But Batala, you confirm?
Sure.
Great. But here, now you look calculator.
Yeah.
Oh, in the function, you just check to make sure it's in degrees.
Yeah, it's okay.
Awesome, thank you. So what this means is that if this slope is 90 degrees, then that's free fall, which is very rare. All the slopes we know, they can be something between 0 and 90. So we leave it like that. It can be mg sine theta or w sine theta. Then L.
Huh? Okay.
All right, thank you. Next, so we have a question here which we are trying to solve. First of all, for emphasis, we are saying R. It's talking about the air resistance. We can call it RR, meaning, let me just try to write it. If I was to do that, it will look like this. Okay, so tractive effort is equal to, oh sorry, let me put it where I want it to be. So tractive effort of simply E is equal to rolling resistance or friction resistance plus, oh sorry, plus C mg or simply W sine theta. I'll try to use a 0, or let me just do this theta, then plus the air resistance, then plus C, the accelerating force. These together, they are giving us the tractive effort. These are the resistances, the forces that are opposing the movement of the vehicle. So together, this tractive effort, meaning when the engine is running, it should overcome all these. Then you see your engine accelerating. Now, if you look at the next one, the question that we're having, which is trying to apply this, it says, calculate the work done by an engine pulling a train of weight 1 meganewton at a constant speed for distance 1.5 kilometers if the frictional resistance on this level track is 4.5 newton per kilonewton weight. So if you look at the last item given, it says 4.5 Newton per kilonewton, and we've been given the weight is 1 mega Newton. So to make things easier for us, we have to convert this to newtons and also to kilonewtons. So Mr. Batala, what does mega represent, capital M?
It represents 6 zeros.
Excellent. 6 zeros. Or Mr. Chewa, if I say 10 power 6, am I correct?
Yes, sir.
Excellent. So this is the conversion we have here. There is 1 million newtons. And let me just pick it. This is the one here. So here we've just done the conversion. Then the distance is 1.5 kilometers. We can't leave it in kilometers. We want it to be in meters. So again, a kilo is 1,000. So we multiply 1.5 by 1,000. The answer gives us 1,500 meters. We are looking for the meters. Now, the other one we said, this 1 million newtons, we don't want it to be just like that. We need to make use of this, the 4.5, to calculate the frictional resistance. So what we do is to convert the 1 million newtons into kilonewtons. And the way we do it is just by dividing by 1,000. So this is what we have here. Meaning 1 and the 6 zeros divided by 1,000. Then this is now converted to newtons. Now, we have the weight in kilonewtons. We also have the rolling resistance, where we've been told that it's 4.5 kilonewton, or rather 4.5 Newton per kilonewton. So what we need to do is simply to multiply that 4.5 by the total weight in kilonewtons. Then the kilonewtons will cancel, and what you have is the answer in newtons. So this one and this one, they go away. In 4.5 times 1,000, we have 4,500 newtons. This one is the frictional resistance, which we are calling R, or rolling resistance. Others use that. That is the term which may be used from time to time. So away from rolling resistance. Now, one thing I have to emphasize is that this rolling resistance, sometimes you'll be told that it's 30% of the total weight. Then you calculate it before you start using it. Or the way they've done it, 4.5 newtons per kilonewton, or they will say a certain number of newtons per ton, and then the weight, the total mass of the body is given in tons. So the interpretation still remains just like that. Now, first thing we do there, already here, I think that was a critical part of this, the data. Next, we can try to work this out. What we know about work done, the general formula for work done, so I'll just put it here. We know that work done is force multiplied by distance. In this case, the force is the resistance, or the rolling resistance. The question has already told us that calculate the work done by an engine in pulling that. But before I even do that, there's something I want us to be clear about. Here we're just calculating for work done. All the other forces are silent, so we don't even need to struggle. But as we go, we'll see other situations where this may be twisted differently. So force times distance, and the force we are having is R. According to our data, This is like our rolling resistance, the one we got here, 4,500. The next thing we do is the R, we substitute, our R is 4,500. So 4,500 there. The distance, this is the one we converted here, 1,500. So 4,500 times 1,500. Now let's multiply the two. Mr. Batala, does it give us that number there? 4,500 times 1,500. Mr. Batala, Mwapwete calculator? It's correct, thank you. So if you look at the question, they said calculate the work done. They didn't tell us the unit, so we can leave it like that. Or we convert. I don't encourage converting if you haven't been taught, because sometimes that's how people again end up making mistakes after the conversion. Right. Let me pause there. Any questions first of all? Mr. Batala, any questions? Are we clear? Okay. Then, Mr. Chewe, are we going to proceed?
Yes, sir.
All right. Okay. Next, we have the second question. Good. We think we have three of them. The second question is saying a car having a mass of 2 tons is driven up an incline of 1 in 10. Sign, not the way they put in sign. This sign, we prefer to write it just to sign SIN. That's N. At a constant speed of 72 kilometers per hour, the resistance to the motion of the vehicle is 25 newtons per ton of the mass. Determine the tractive effort required and the power developed. Okay. So first, the mass is 2 tons, and we want this mass as 2 tons like that. It's okay. Then the mass, the SI unit is kg. So 1 ton represents 1,000 kg. So all we do now is to multiply that 2 by the 1,000. So we have 2,000 kg. Now that we have the 2,000 kg, we move out from there. We'll come back to each zone. The next thing you can see is, let me even try to draw this for us. It's saying the incline is 1 in 10. Now the interpretation is like this. You use a right angle triangle. So this is 1, and this is where the 10 is. Let me just put it there. This is 10. And this, put it there, that's 1. So if I'm saying that this is right angled, then I'm trying to locate this angle here, the theta. So what is the ratio between 1 and 10? 1 is the opposite, 10 is the hypotenuse. What do we call that ratio? Opposite over hypotenuse? Is it sine or cos? Excellent. So Katoa, sine is opposite over hypotenuse. So in this case, the opposite is 1, and that is 10. So that's why if you look at the question, they had already given us a hint that this 1 in 10, the gradient that we're having is actually sine, and we don't need to struggle with it. Next, so meaning we write it like that, sine theta is 1 over 10, and we just leave it there. We don't need to get the actual angle, because we are going to replace it as one complete number. Next, we have 72 kilometers per hour, which we should not leave in that format. We have to convert it to meters per second. When you're multiplying, when you're converting to meters per second, you convert first the kilometer by multiplying by 1000. Then the hour, we divide by 3600 because we are converting them to seconds. So 1000 over 3600. In short, this is where we say it's as good as dividing by 3.6. So 72 by 1000, which is 72,000, divided by 3600. Does that give us 20? Is that correct? Mr. Batala, are we winning? Is it adding up? Not shukire na calculator rero. Excellent, thank you. The next one, this one is saying the resistance to the motion of the vehicle is 75 newtons per ton. Newtons per ton. And we have two tons. So all we do is multiply that 75 newtons per ton by the 2. So the T, the ton, these two cancel. Then you remain with the newtons. So 75 times 2 multiplied by 2 rather, that gives us the 150 newtons. This one is talking about friction resistance, the friction between the tires and the road surface. So we have the rolling resistance. Next, let's get the gradient resistance or the resistance because of the slope. So this gradient resistance is the one we call W sine theta. Now this is where it becomes interesting because this weight we have, or do we have it? What we have is the mass. So instead of leaving it as weight, we might as well expand it. Expand it as mg. It's still the same. So mg sine theta, or if we want, we can find the weight in the data, then come back and replace. But here we proceed. We simply say m multiplied by g. Then we have the sine theta. So we just done the small expansion. Then we're saying equals. So what we do now, the mass is 2 tons. So in that case, we're not going to use the 2 tons. We use the one with the SI unit. So we use the 2000 by G. The G is 9.81. There it is. Then here, this is the one I was trying to emphasize. If you look at sine theta, the whole sine theta equals 1 over 10. So where is sine theta? Here, where we have sine theta, we are going to put that number 1 over 10. So we have 2000 by 9.81 by 1 over 10. Meaning whatever number we get after multiplying 2000 by 9.81, we just divide it by 10. So there, does it give us 1962? Is that also correct, Mr. Batala? Well, mwaba tukwetikakireta rero.
Yes, sir, it's correct.
Okay, thank you. All right, then let's pick up. So here, if you look at this one, there's one more thing that hasn't been mentioned. The, the machine, or rather this car is running at a constant speed, meaning it's not accelerating. At the same time, the air resistance, nothing has been mentioned. So those are the two items which have been mentioned there. So we're saying air resistance, which we've been calling as AR. We haven't been given anything, so it's 0. At the same time, accelerating force, which is actually F. We also have nothing. So here, let me just put it below there. So these two are blank. We leave them like that, no problem. So that's what we're emphasizing below there. Now we can write the equation in full just like that. We said the tractive effort should be able to overcome the friction, the loading resistance, the gradient resistance, and the air resistance, including the accelerating force. But you check, you will notice F is 0 and air resistance is 0. So which just leaves us with the two of them. The loading resistance, which is the friction resistance, or R, and the gradient resistance. So from what we calculated up here, R is the one we have here, the 150. So I wake up at the 150. Then gradient resistance, the resistance because of the slope. The upper number, this is the one coming out as 1962. So all we do now is just add them. We have 150 plus 1962. What does that one give us? Or does it conform? Is it agreeing with the answer we have below there?
Sure, sir.
Awesome, thank you. So E is 2112 newtons. Now here, power, the way we know it is it's supposed to be, let me just write it. The normal formula for power that we know is work done divided by time. Now, this is not always the case. There is also another shortcut formula for a machine which is moving at a constant speed. When a force has maintained a constant speed, we're able to use, because we already know that work is force times distance. So if you now decide to say this whole thing over, we'll say, supposed to be over time. You notice that the last part, distance over time, gives us velocity. So that's why in the end, this becomes Fv, force times velocity. In this case, the force we are using is the tractive effort. So therefore, what we have now is the power is equal to E multiplied by V. Of course, not electric vehicle. Tractive effort multiplied by that constant velocity V. So we check back in the data, you will notice the information has been provided. We already have this tractive effort, 2112. Then the velocity, the constant velocity at which it's running is 20. meters per second. So we multiply 2112 times 20. Again, Mr. Batala, what does it give? Is that answer still correct? Thank you. So that's 42,240 watts. Now, once again, we emphasize here that with the unit, you have an option. It's either you can say my power is 42,240 joules per second, or watts. It's the same thing. No hard and fast rules there. You can use them interchangeably. There is no problem. Okay, Mr. Chewe, are we together?
Yes, sir.
Okay, great. Mr. Batala, is that okay?
Sure, sir.
Thank you. Can we pick up the third one?
Yes, sir. We can proceed.
Right. Now this one, okay. Yeah. So it's a bit interesting. It says we have a real engine having a mass of 30 ton, moving on a level track with a constant speed of 50 kilometer per hour. Then we've been given the friction resistance, 80 newtons per ton, and we also have the efficiency of the engine, which is 85%. Then we want to find the power of the engine. Okay, so from the information provided, we start first of all, we have the mass. The mass is 30 tons. We cannot just leave it in tons, we also need to convert it in 2 kg. So we say 30 times 1000, we have 30,000. So that is our mass. Next, the velocity provided, which is 50 kilometers per hour, should also be converted to meters per second. So we say 50 kilometers per hour times 1000 divided by 3600, the same thing. Once again, let's confirm that one. Bruce, is that answer correct? Oh, sorry, 13.888. Is that okay? Meaning 50 divided by 3.6 or 50 by 1000, then you divide by 3600.
It's correct, sir.
Okay, thank you. The other one that we need to fish out is the frictional resistance, the one we're calling R. We were told it's 80 newtons per ton and the total tonnage is 30. So all we do is multiply the 80 by 30 to get rid of the tons and we get the R. So when you multiply 80 by 30, it's like 8 times 3 is 24. Then we put the 2 zeros. So it should be able to give the 2400 newtons. So that becomes our rolling resistance. Now, this is a very funny question. If you look at the resistances provided, it's a level track. That's why they have not given us the slope. And if it's a level track, it means that issue of gradient is out. Air resistance is silent. Yes. So for the resistances, we're just fighting the friction between the wheels and the rod. The next thing we have there is the efficiency of this engine, which is 85%. 85% means 85 over 100, which is 0.85. We'll see which one we can easily enjoy working with. So we can either use 0.85 or 85 over 100. The interpretation is the same. That is the information that has been provided. The next thing we can do now is okay. The next thing we can do is just to make sure that we get the general formula together, which in this case is the active effort equals that resistance added to W and theta added to AR and then plus F. In other words, we are saying the resistance to motion, the resistance because of friction, plus the other resistance because of the gradient, plus the other resistance due to the air, plus the other opposing force due to a machine or the body accelerating, increasing its speed. Analyzing this has already told us that air resistance is zero. We haven't been given the factors there. The accelerating force is also zero, and it's on a level track, so the gradient resistance also comes to zero. Now, with this information applied there, you will notice all these, starting with this cancelled, gradient is out, air resistance is out, and this one is out. And hence, the tractive effort is equal to the resistance. So what do we do next? We just multiply, we just substitute. This effort is equal to this. So there we are. The tractive effort required is just going to be 2,400 newtons. Of course, that's in newtons. Now, the power, like we did earlier, we're just now going to go through the same again. The power is going to be the tractive effort multiplied by the velocity. So this is 2,400 times what we had there. 2400 times 13.888. Okay, now 2,400 times 13.888. Mr. Batala, is that answer still correct? Or do we need to edit?
It's correct, sir.
Correct, thank you. So here we can now say what we have is that power which will reach last. Now the question is saying calculate the power of the engine, meaning what power is coming from the engine, because the one we've calculated is the net power that we need on the output. So what should the engine do? How much power should come from it? So this is where we now explore the formula for efficiency. The formula for efficiency for such is net power over gross or actual power coming from the engine, expressed as a percentage or times 100. So here we're saying 85. When we start substituting, the percentage is 85 is equal to the net power is this answer we have here. So it's 33,331.2 over the gross power. Then we're multiplying by 100. Here we've just put 85 there because there is this 100 here, no problem. It's as good as the 100 was down there. Then we've just cross multiplied. So all we can do now is just make gross power the subject. And this is what becomes of it. We have 33,331.2 divided by 85. Then multiply it by the 100. So once again, let's see, does that give us the number below? Mr. Bruce, you can still confirm for us. So 3333 again 1.2 times 100.
It's correct, sir.
Oh, thank you. Now here my emphasis is that if you look at the way we wrote the data, we said the efficiency is 0.85 or 85 over 100. So if I was to go that way, I would write it like this: 0.85 equals, then I go ahead with the substitution, which is 33,331.2. Of course, I'm going to multiply by 100, but we're dividing by this other one, which is gross power. So right there, gross power or actual power. So here, if I have to make something the subject, it is gross power, and I will end up like this. It will be my gross power is equal to, what will happen if I make gross power the subject of the formula for this one? What should I have on the right hand side? Oh, sorry, by the way, I'm not supposed to multiply by 100 here. It should just be the way it is. So, on the other side, of course, the 100 has been taken care of by the 0.85. So, if I have to make gross power the subject, because what I have there is 33,331.2 divided by gross power. It's like I'm just cross multiplying. I might as well do this. I would say this over 1, and of course here they're also dividing. So what will happen is that I will have this. Let's go back. It becomes this same 33,331.2. Then I'm dividing by the other number which was there, which is 0.85. 0.85, 0. Okay, then what happens? So 33,331.2 divided by 0.85. What does that give us? Actually, What answer is it giving us? Are we still on the safe side? Is it giving the same thing? Push. Mr. Batala, you there? Okay, maybe could be an issue with the network. Alright, so this one is supposed to give us the same thing because what you see there, 100 over 85 is 0.85. So what we should get is the same answer we had earlier. The one confirmed 39,213.176. And this is power, so it will be in watts. Meaning the engine should give us 39.213 kilowatts in order for us to have the actual power on the output being 33.331 kilowatts. In between, we will have those losses happening, which are very normal for Okay, let me pause there. What I have here is an exercise, just having 4 questions, which we can try out. And feel free now to pick out any questions coming in a variety of past papers or under this topic. Tomorrow, I want us to fish out either this one, what do we call this, simple harmonic motion or balancing of masses. See which one will be faster for us. Mr. Tewe, any questions? Or are we clear?
For tonight, sir, tomorrow is the lesson.
Yes.
You say tomorrow the lesson because
Tomorrow I was proposing, is 16 hours workable for us? What time is okay for us?
maybe just 20 break from me because the shop that is open.
Yes.
Maybe the break down that I'm attending to. So if it's at 16 hours, then I will take it.
You will miss. All right. So we maintain the one we've used today.
So, sir, I don't know from other guys.
All right. Okay. That is noted. Mr. Patella, I hope you're still there. Do you have a counter proposal to that?
No, sir, I think 20 is okay.
Okay, great. So then it is set. We can have another one tomorrow, 20 sharp, and then we'll continue from there. Okay, I think for today, Mr. Batala, any questions or is everything okay? Okay. Okay, thank you.